Hi, my name is Ron Wade. I am a principal systems engineer in the timing division of Renaissance Electronics, and I am happy to introduce you to this PCIe reference clock jitter series of videos. After watching all of the videos, you'll have a working understanding of SERDES building blocks and jitter transfer functions. You'll understand PCIe common clocked architectures, PCIe independent reference clocked architectures, and also PCIe transport delay and its impact on jitter. Finally, you will have a working understanding of this famous diagram from the PCIe base specifications and where it came from. So the agenda for the series of videos is as follows. We're going to start out with what is PCIe, and then we will move into the SERDES physical layer building blocks and their jitter transfer functions. And then we'll move into the PCIe common clocked, independent reference clocked architectures. Then we'll touch base and explain PCIe transport delay. And then finally, we'll build the PCIe reference clock jitter model. So let's get right into what is Peripheral Component Internet Express, shorthand PCIe. Okay, well, PCIe is a SERDES interface. It's a high-speed serial interface. It's used primarily for communication within a motherboard or within a system board, and it connects multiple peripherals to the CPU on the main board. It is low latency, about 500 nanoseconds round trip. All PCIe from Gen 1 through Gen 7 has a defined bit error rate of 10 to the minus 12 for high reliability applications. This bit error rate is baked into the specification. Because of the history of basically connecting things on a single board, PCIe has limited reach. It's approximately 14 inches without the use of what's called a retimer, and it was not originally intended to drive cables. The PCIe clocking tends to be common clocked, and we'll talk about that later. Spread spectrum is usually used due to the historical nature of PCIe. And the critical timing parameters are the phase jitter of the clock after applying the appropriate PCIe filters and the transport delay or phase delay in common clock systems. I've highlighted in yellow here what I'm calling PCIe segments, which are sort of self-contained little PCI Express interfaces within a system. Here we've got one that connects the CPUs to some switches and to each other. We've got a PCI switch here that then connects NVMe SSD drives in this drawing. We also have over here a switch which connects to two Ethernet adapters, and then it connects to another switch which has miscellaneous devices down here. So I'm calling these yellow items segments. So the characteristics of PCI Express are, first of all, it's full duplex point to point. So there's dedicated transmit and receive bandwidth, and that bandwidth doubles with each generation. The PCI Express interface is scalable in width. Each interface is called a link, and then it may have multiple numbers of lanes. So by one is the smallest, one lane, which is one transmit receive pair. You can go all the way up to 16 lanes, which is 16 transmit receive pairs in one link. Scalable via generations. Gen 1 and Gen 2 used 8B, 10B encoding, which means that for every 10 bits sent, only 8 bits were the actual data. So the 2.5 gigabit transfer rate was really 2 gigabits of usable data, or 2 gigabit transfers of usable data. So the 5 gig was actually only 4 gig of usable data. So 2 to 4, and then when we got to Gen 3, the encoding scheme of the data onto the serial bus changed from 8B, 10B to 128B over 130B. And this is essentially zero overhead. It's a super small percentage, but it rounds to basically no overhead. So this 8 gig of transfers per second is actually 8 gig of usable data. So we had 2, 4, 8, 16, 32, 64, and Gen 7 is 128 gigatransfers per second per lane. So you can have up to 16 of any of these in the interface. The other thing about PCI Express, it is software and hardware compatible from generation to generation, which is one of its great strengths. So the other great serial interface in the world is Ethernet. And let's compare Ethernet and PCI Express. And we're going to use this island chain of Hawaii as an example. So Ethernet has a much longer reach than PCIe. It's designed to drive cables of various types, the most popular being RJ45, and its reach is measured in tens to hundreds of meters, depending on other variables. On the flip side, the bit error rate is not specified, and a higher latency of 3 microseconds is typical, and that's partially due to the longer distances involved. And it has lower bandwidth than PCI Express, especially as PCI Express moves up to 8 lanes or 16 lanes. But it is the standard for bridging between devices across networks, or between motherboards in a rack. Ethernet clocking uses separate clocking. There is no clock in the Ethernet cable. Spread spectrum is not used, and the critical timing is usually phase jitter, unfiltered, usually between 12 kilohertz and 20 megahertz. And then, because this is always separate clock for Ethernet, transport delay does not apply. Later on, we'll show why that is. So here I've got the islands of Hawaii, and we have PCI Express on each island. So all the communication within each island is taken care of by PCI Express. And then on the main island, the big island of Hawaii, we have an Ethernet switch. So this system connects to Ethernet, and then the switch sits here and is connected to all the other islands. And so that's how all of these would communicate with each other. That's the analogy that I've got. I think it represents the essential differences between the two. And that's it for this first module. So thank you very much. I appreciate your time, and be on the lookout for the remaining videos in this series.